Hello dear students, welcome you all. So in this lecture I am going to discuss about the properties of nuclear forces. So you know very well that in the previous lectures I have discussed about the meson theory or Yukawa theory of nuclear forces. We have also discussed about the working of the color forces, right, that are responsible for holding the quark inside the hadrons. This was the theory of color forces, and meson theory was the theory that explained the stability of the nucleus, and according to it neutron and protons are held together inside the nucleus because of the exchange of mesons, right. So these are the two theories, right, that are applicable for explaining the forces that are operative inside the atomic nucleus. We know very well that at present we have four fundamental forces in the nature. We start with the very simple one, that is gravitational. Although I am calling it as the very simple one, but it is very complex force in the nature. This is the force that till today we are not able to explain correctly, right. So gravitational, then we have electromagnetism, then we have strong nuclear force, and we have a fourth one, weak force. Now out of these four forces, these two forces are operative inside the atomic nucleus, we know very well, and these two forces are of very long range. So they operate up to long distances. Their range is taken as infinity, right. So I'm just talking about the strong nuclear force here. We know this force is the strongest force in the nature, right. If we take the magnitude of gravitational force as 1, right, then this electromagnetic force is 10 raised to power 36 times stronger than gravitational force. Strong nuclear force is 10 raised to power 38 times stronger than gravitational force, and weak force is approximately 10 raised to power 13 times stronger than gravitational force. So this is the comparison. So you can see from here that the nuclear force, this strong nuclear force, it is the strongest force in the nature that we observe, right. But this force is actually a force that acts only in the very small dimensions. This force is operative only when the distance between the interacting particles, whether they are quarks or they are hadrons, it is of the order of 1 to 2 Fermi, right, or you can say 10 raised to power 15 meter. This is the dimensions of the atomic nucleus. So this force work only in such a small volume, right. But when we look at the larger dimensions, then we don't observe this force, right. In large scales we observe only gravitational force and electromagnetic force, right. So here now I'm going back to these two theories, right. Meson theory of nuclear forces and color forces, the theory of color forces that I discussed in the previous lectures. So if we talk about the nuclear force, then nuclear force can be divided into two subcomponents, right. The one force is that force that we calls fundamental strong force, right. This force is the force that is operative between the quarks, right. This is called fundamental strong force or color force, right. This force is responsible for holding quarks together inside the nucleus, inside the neutrons and protons and mesons. We know very well quarks made hadrons, baryons and mesons. So this force is called fundamental strong force, right, and it is operative. Fundamental strong force is operative up to a distance of 0.8 Fermi, or we can say up to 1 Fermi maximum, right? It means it is working inside the hadrons, either neutron or proton. But this force also has a residual component, right? Only small component we can say. That residual force, we call that force as residual strong force. That force is operative between the neutron and proton inside the nucleus, or we can say between neutron and neutron, or between proton and proton inside the nucleus. This is residual strong force, or sometimes we call it as simply nuclear force. But they are, both are same thing. They are strong nuclear forces, right? But we can classify them in two groups, right? One is fundamental strong force, that is scalar force, that is operative inside the neutron or proton, right, for holding quarks together inside these particles. But the other one is residual strong force, that is responsible for holding neutron and proton together inside the nucleus. This is responsible for the stability of a nucleus, right? So these are the two forces, and this force, residual strong force, it is operative up to a distance of 2 Fermi, or we can say its range is from 1 to 2 Fermi, right? This is the range, right, of this residual strong force, right? So this is about the color force and residual strong force. This residual strong force is actually responsible for this holding neutron and proton, and this is what we have discussed here, meson theory, right? Residual strong force act between neutron and proton, and it arises when there is an exchange of meson between the neutron and proton. That was meson theory. We have already discussed here in the previous lecture, right? And from where these mesons are coming, we know meson is a combination of a quark and anti-quark. We have seen it in the case of working of color forces. I have told you there that if I strongly pull one quarks out of the proton or neutron, then in that case I will not get a single quark, but I will get a pair of quark and anti-quark, and this pair is nothing but it is a meson, right? So when these mesons exchange between neutron and proton, right, then this force is responsible for holding neutron and proton together inside the nucleus, and that is the meson theory that was given by Hideki Yukawa, right? We have already discussed it, right? Now I am showing you one animation, from that you can understand it correctly, right? You can see here, this is atomic nucleus. You can see here, I am showing you atomic nucleus. You can see here, this is atomic nucleus. There is proton and a neutron inside the nucleus. Now let's go further. Now this is what? This is proton, right? And I have told you that these protons are held together. I can show you once again. This is nucleus. This is proton, right? So you can see here, inside the proton we have a up quark and a down quark, and these quarks are held together due to the exchange of gluons, right? I have explained it. These gluons carry a color and an anti-color, right? So there is continuous exchange of these gluons among the quarks, and these quarks are held together inside the proton, right? And this force is called color force, fundamental strong force, that I told you in this lecture. Fundamental strong force, right? It is responsible for holding these up and down quarks inside the proton, right? Now let's see what happens if I have two protons, right? You can see from in this animation, right? So in this animation, you can see that now you can see here. This was the thing that I was telling you, that when these two protons are very close to each other inside the nucleus, then in that case there is a possibility that one quark can come outside from this proton, and in that case I will get a pair of up and anti-up quark, and then that is obviously a meson. This will be absorbed by this proton, right? So then in this way these proton and neutron will exchange their character. This was the meson theory, right? So this force is called residual strong force, right? This thing is continuously happening inside all the neutron and proton inside the nucleus. You can see once again, right? So this is the working of these color forces and this residual strong forces. I am showing you one more animation here. You can see now the thing is very clear. You can see here that this is proton, this is proton. So you can see this is proton, this is neutron. So they are continuously exchanging, right? These mesons, right? And due to the exchange of meson, the color of the quark is continuously exchanging inside the nucleus, inside the neutron and protons also. So this is the way of working of residual strong force, right? You can see the meson is continuously emitted and absorbed by these, two hadrons, that is proton and neutron. So this is the way of working of this residual strong force, right? I hope that the thing is very clear, that what is the difference between fundamental strong force and residual strong force. Now I am coming to the some properties of a strong nuclear force. The first property that I discussed here, that it is the strongest force in the nature, right? It is even stronger than the electromagnetic force, right? You can see here it is 100 times stronger than electromagnetic force, right? Nuclear force is a short range force, right? Now I can draw a graph here that will make the things very clear. This is the plot of strong nuclear forces with respect to distance, right? Overall, I'm talking about the overall nuclear forces. It includes both color forces as well as the residual strong forces. So if I plot a graph between the force and the distance, right, between the two nucleons, right, that is neutron or proton, this is R, then I got a graph of this type. Right? This is the graph, right? Now you can see here in this graph, this is if this is 0, this force is positive, means repulsive, and here it is negative, means the force is attractive. I can write here attractive and repulsive, right? So you can see here, as the two nucleons come together each other, right, the distance is decreasing, so the attractive force go on increasing. It becomes maximum when the distance it is maximum here. You can see here it is maximum here, right? So it is maximum between the two nucleons when the distance between the two nucleons is of the order of 1.5 Fermi, right? After that it is maximum at this point, and if we further come close these two nucleons, right, like this is a proton and this is a neutron. So these are coming close to each other, right? They are attracting due to this strong nuclear force. But when the distance between them becomes less than 1.5 Fermi, then this force start decreasing, and ultimately at the distance of this distance is 0.5 Fermi. When we reach at this distance, then the force becomes 0, right? This is very important. Otherwise, what will happen? These two nucleon, neutron and proton will come very very close to each other, and they will overlap with each other, and that will destroy the stability of the nucleus. So this is not possible. They can't come close than this limit, right? When the distance is further decreased, if we further go toward this side, then the nuclear force becomes repulsive. Now you can see from the graph, it is repulsive here. It is attractive only when the distance is greater than this limit, and it is maximum at this point, right? If the distance is further increased, then at a distance of nearly 2 Fermi, right? This is the distance, that is 2 Fermi. At this distance, the nuclear force are nearly equal to 0, right? So this is the graph that tell us that the nuclear forces are very very short range forces, right? The another property is nuclear forces are charge independent, right? We know very well that these forces does not depend upon the charge, right? These forces can exist between a proton and proton. They can exist between a proton and neutron. They can exist between a neutron and neutron. So all the possibilities are equal. There is no difference. If I take a proton-proton pair, proton-neutron pair, neutron-proton pair, neutron-neutron pair, all the possibilities are same, right? Nuclear forces don't make distinction between the particle on the basis of their electrical charge, but they operate between the nucleons on the basis of their color charge. That I have explained in the earlier lecture, that all the nucleons in addition to electric charge contain a quantum property that is called color charge. So this is this color charge is responsible for this interaction, and it has nothing to do with the electric charge, right? So we can say that this nuclear force is charge independent, right? Now another property that I want to explain you, that these forces are spin dependent, right? Spin dependent. It has been observed that the nuclear forces depend on the spin of interacting nucleons. If they have parallel spins, then this force is strong, but if they have anti-parallel spins, then the force is not so strong. So we can say that the nuclear forces are spin dependent, right? The next property is they are non-central forces, right? We know what are central forces. Gravitational force is the classical example of a central force. Although electrostatic and magnetostatic forces are central, but electromagnetic is not central force. We have already studied it in electrodynamics, but the gravitational force is fully central. Here the strong nuclear force is also non-central. It has been observed that it is partially central, partially non-central. So this is also the property, or we can say simply that it is non-central. We have only one fully central force in the four fundamental forces, that is gravitational force, right? Now the next property is their saturation property. It has been observed that the nucleon can interact with only certain number of nucleons in their neighborhood, right? This is the central nucleon. Around it we have another nucleons, right? This is the atomic nucleus. So in the neighborhood of this central nucleon, we have number of other nucleons, right? Now according to the saturation property, it is believed, it is explained in fact, that this nucleon can interact only with the certain number of nucleons around it, right? And that's why binding energy of the nucleus is directly proportional to the mass number. The force that is responsible for holding these nucleons together inside the nucleus. If this strong force that bind the nucleus, it is not saturating, right? It means it is acting between the all pair of nucleons inside the nucleus. So in that case, this binding energy should be proportional to the number of pairs, that is A into A minus 1 divided by 2. This is the number of pairs that we can obtain by simply applying the formula of a combination, right? So if a nucleus contain A nucleons, then I can form the number of pairs that will be given as A into A minus 1 divided by 2. So in that case, the binding energy will be directly proportional to, if I ignore 1, A square. So, but it has been experimentally observed that the binding energy of the nucleus is directly proportional to mass number. It means the one nucleon, right, it can interact with only a limited number of nucleons in its neighborhood. It can't interact with all the nucleons present inside the nucleus, right? So this is called as the saturation property of nuclear force, saturating property, right? This is the next property. Now the last property that is these forces are of exchange character. So we have already explained that during the operation of this nuclear force, a particle is exchanged. If I talk about the color force, the particle exchange is a gluon, and if I talk about the residual nuclear force, the particle exchange is a meson. So this is all about the properties of the nuclear forces, strong forces, how they operate inside the nucleus, and how they are separated into sub streams, we can say in that way, that one is fundamental strong force and other is a residual strong force, right? So thank you very much.